Let me talk through this picture. You have your system under test, so something you want to fuzz, but just having your system is not enough. You need to be able to put inputs into that system and get coverage out of that system. So combine these three things: system under test, inputs in, coverage out. I call this fuzz target, and it is different from system under test. It's more than system under test. Once you have this fuzz target, you can create the fuzzing loop where you start from a seed corpus, you feed it into your system, it produces coverage for your seed inputs, and then the brain of fuzzing, which I call fuzzing engine, decides which inputs to keep in the corpus, which inputs to discard, and then it also decides which inputs to feed to the mutator, and then the mutants will be fed back to the fuzz target. So coverage is used in two very similar, maybe it's actually one common thing, in two similar ways. First of all, we decide whether to keep an input in the corpus based on coverage, and we also decide which input to mutate. Sometimes we do it based on the coverage. By the way, as you've noticed, I didn't actually define yet what coverage is. I'm just saying there is something called coverage. Empirically, we probably will all agree here that guided fuzzing is stronger than unguided. So when we first started using coverage to guide fuzzers in 2011, maybe, we saw, wow, this is so much stronger. But now everybody uses coverage guided fuzzing, so it's not a surprise for anyone. But the funny thing is that guided fuzzing is unguided most of the time, because once you have reached all available coverage and you don't reach it anymore, you're not being guided at all. And I would say that 99% of our fuzzing at Google is not guided. It was guided in the beginning, but now it is not. I think you see these blue dots on the screen. So I want to make this small cartoon about fuzzing. We start from initial corpus. We have our system under test. We have some sample inputs, and these inputs are depicted here as blue dots. And when we fuzz, we take one of those inputs, maybe several, start mutating them, and the mutants are typically somewhere close to the original, because this is how we produce mutants. We flip bits or change the data fields, etc. So we have produced this cloud of mutants around one of our inputs, and one of those inputs happens to generate new coverage, and so we have this red smiley face. We add this new input to the corpus, and so after this first round of fuzzing, our corpus now has 4 elements, one of which is just freshly added. And rinse and repeat, we do the same process every time, and eventually we add more and more and more inputs to the corpus until we don't. So what happens when we have exhausted all the coverage signal that is available for us? Our fuzzing becomes unguided. We keep mutating. We mutate and mutate and mutate, and nothing happens. Our corpus stays the same. We don't detect any new bugs. We just waste CPU cycles. This is the state where we are in 99% of the time. What is the problem? So most of the mainstream fuzzing engines, if you wish, use coverage signals such as control flow edges, basic blocks. You can call them anyway, but this is a signal based on control flow, and control flow, the size of the control flow is proportional to the size of your program. And even if your program is very big, the control flow is still as big as your program, not bigger. And you eventually will cover all the control flow. If you're lucky, of course, but you'll probably even cover less than that. And with the traditional guided fuzzing, if you have n different edges in the control flow, your corpus is not going to be bigger than n. Many fuzzing engines, SiliFuzz, AFL included, use some other signals that are even common between those engines. I would mention two. One is counters on edges. This is like, okay, it's interesting whether this edge has been executed once, twice, or 3 times. And also value profiles. What were the arguments of this comparison instruction, but we bucketize them in small numbers. But in the simple way they're typically used in FUZZer, AFL, FL++, etc., there's still these signals are proportional to the size of your application. They have a large constant multiplier, like you will have 8 times more counters than you have control flow edges. And even with that small constant multiplier, you already start seeing all sorts of scalability problems with FUZZer and AFL, etc., on big targets. So what we want is some kind of very dense or rich coverage signal that will allow you to have many corpus elements that are as diverse as possible, but then you still want your fuzzing to fit into your CPU, RAM, disk, and whatever else is your resource constraint. The problem with rich or dense coverage is, first of all, collecting anything that is more sophisticated than control flow is expensive. So your single run becomes more expensive, usually by a constant multiplier, but still more expensive. If you have more coverage, if you have more diverse coverage signals, your corpus becomes bigger because this is what you want, right? You want many more corpus elements that are diverse between themselves. And then if you have a big corpus, in order to get any benefit from this corpus, you have to keep mutating every element of that corpus. Since it is bigger, you have more runs. And this snowballs quadratically, exponentially, however you like. And of course, the result is more CPU, more RAM, more disk. I don't know, do we care about any other metrics? But these 3 are expensive enough. That's CPU. These calls are CPU. So the question, are these rich coverage signals actually important? And my initial problem statement was not like this. It's not that I thought, is rich coverage signal important? My initial work was, no, we have a business problem and let's figure out how to solve it. And 4 years ago, my hypothesis was that to solve the business problem we have, we need rich coverage signal. And so the few following slides are the case study of SiliFuzz, a project which we thought needed rich coverage signal. And we kind of sort of confirmed that it indeed needed it. It is by no means scientific. It is more like anecdotal evidence that this project benefited from rich coverage signal. So what is SiliFuzz? SiliFuzz is a project that is 3.5 years old by now. Its goal is to detect bugs and defects in the modern CPUs. And this distinction between bugs and defects is important for our project. Bug in a CPU is a problem in the design, and so it will affect a family of CPUs. If you have a specific family of CPUs from a given vendor, all of those CPUs will have the same behavior that is not according to the spec. And so far we found several. I think two of them are public by now, and one of them is mentioned on the slide. We found an instruction sequence that will cause a specific AMD CPU family to hang. So you don't want this behavior in, especially in the cloud environment. So this is supposed to be a major thing. CPU defects are something completely different. CPU defects is a situation when a single physical object is damaged on some low electrical level, physical level. Maybe some transistor is broken, maybe some wire is broken, who knows? And the typical manifestation of a CPU defect would be just one instruction with maybe some subset of parameters. Like on this slide, this is integer multiplication, where the first parameter is memory location and the second parameter is a specific register. This instruction will miscompute. And in one instance that we found, it just leaves the output register unchanged. And I think roughly 80% of cases that we find with SiliFuzz only affect one core of a given machine. So not all cores on a given CPU, just one of the cores, meaning one wire is broken. That's it. And there is a growing body of publications on this topic. Google published two interesting papers on this. Meta is also doing very good public research in this space. So it's a growing big problem, business problem that we needed to solve. So this problem doesn't have a single solution. There are fault injections and fleet monitoring and software practices and hardware development practices. The SiliFuzz project is aiming at a kind of very narrow part of this business problem, which is to find defective machines in the fleet and evict them from the fleet. We call this approach fuzzing by proxy, which is where we take some piece of software that behaves like a CPU for some definition of like. So it could be a simulator, emulator, it could be a full RTL design that we can replay as a software. It could be even a static analysis thing that looks at the instruction sequences. So we fuzz it in the normal software definition of fuzzing. And the result of that is a diverse set of instruction sequences. So we build a corpus. This is very slow. CPUs are big. CPU models are very slow. So this is a slow, expensive process. And then once we have that corpus of inputs, we have two goals: detect bugs and detect defects. If you want to find CPU bugs, you basically only need one CPU for the family, and you can run all the tests there. If one of the tests misbehaves, you found the bug. It is relatively straightforward, but the bugs are not that frequent. We found a handful, I would say. Defects are more numerous, but in order to find the defect, you have to run your tests generated by fuzzing on every machine there is. And not just every machine, but every core, because the defects are isolated in single cores. By the way, questions during the talk are welcome. So now going back to reach coverage. We were building this infrastructure for fuzzing CPUs for maybe a year, and then we fuzzed the proxies, the simulators we had, plus or minus with SiliFuzz. So we started with SiliFuzz, then we migrated to a prototype-ish thing of something else, but it was very similar to SiliFuzz. You basically took the control flow as the coverage signal. And we found a few bugs, we found a few defects. The bug that in AMD CPU that I mentioned before was found with this relatively shallow coverage signal, control flow of a simulator. And it wasn't actually too hard to find. It was somewhere very close to initial seeds. And then eventually we saturated. We stopped finding bugs, and our rate of finding defects also fell down because we found all the shallow ones, and the deeper ones were hard to find. And by that time, we had more sophisticated machinery to collect and use what we call reach coverage signal. So we added 2 reach coverage signal, and next week we found 2 more bugs and a bunch of other defects. Later on, we added more reach signals. At some point, we added 1 more reach signal to the mix, and we found yet another one. So that's as good evidence I have for reach coverage as you can get. I don't have anything that I can show you more substantial, because I cannot give you Google's production fleet to try fuzzing on and to replicate. This is my answer to your previous talk, right? We want reproduction in scientific papers, yes. How the hell are you going to reproduce this? I don't know. So maybe what we found, Meta can reproduce. Maybe Microsoft can reproduce. Maybe Amazon can reproduce. By the way, SiliFuzz is open source. And if you work in a large company that deals with millions of CPUs, you can use our work directly. If you're not in such a large company, you really need many thousands of CPUs to find your first defect. So it's complicated.
Kostya, what were the rich signals you used?
I'll get back to what are the rich signals in a few slides. So even though it worked for us, we found these new bugs, new defects. Adding this new rich signal caused havoc in our scalability. We've ran out of quotas for disk, for memory, for CPU, all of those things, and we're still catching up to the scalability. So the signal we use is so rich that we're not able to fully utilize it yet. But that's the essence of the work that my third part of the talk is about. Yes.
Curious, after you add a new rich signal, do they come back and improve the original coverage?
Do the rich signals improve the basic signals? In our case, no, because in our case, the basic signal, which is control flow of the simulator, it is fully saturated. So the simulator specifically that we use for x86 is a pretty straightforward machinery which covers all the instructions and all potential things that instruction can do. And we have manually audited it, and we didn't see at least large places where we didn't have control flow coverage. So we believe that it is close to 99% saturation. You cannot improve too much on top of 99%. So no, we think we actually improved the essence of diversity, not the diversity based on the shallow signal. So the fuzzing engine that we use for SiliFuzz, we call it Centipede. And the background for this name is I actually called my team. I have this prototype, it's called DDFuzz, distributed differential fuzzer. But there is just a fresh paper that came out yesterday, which is called DDFuzz. So we have to rename our tool. Please give me a name. And one of my colleagues told, okay, so this is a bug-eating, highly concurrent software. It's Centipede, many legs and carnivorous predator that eats bugs. And a couple of weeks ago, I told my daughters, like, you need to have images for my presentation. This is from my youngest. This is like, I'm small Centipede. By the way, Centipede, the Centipede project has been merged recently with the open source project called FUZZ test, which Laszlo leads. And if you haven't heard about FUZZ test, I highly recommend you. This is the way for users to represent the fuzz target in a very user-friendly way. And these projects are starting to work closely together. But in the context of SiliFuzz, Centipede is just used separately without fuzz test. Okay, so what are the Centipede's goals? Of course, we want efficient fuzzing. Everybody wants it for anything. Like anything you want to fuzz, Centipede is supposed to handle that in any language, or maybe even not in the language in usual sense. One part of Centipede ensures that it is SiliFuzz compatible. So if there is anything you can fuzz with SiliFuzz, you can fuzz with Centipede. It should support in-process and out-of-process and even remote targets. So if your target is on another network computer, Centipede can still fuzz it, no problem. And of course, the main meat of Centipede is scalability. We wanted to handle rich coverage with an order of billion different coverage signals, or billions, many billions. And as a consequence, it has to handle a corpus of inputs, which also counts in billions. And in order to do all of this computation, the engine has to be massively distributed. Threads on a single machine are not enough anymore. It also has to be stateful, such that if we restart fuzzing of the same target, for example, if our job has been evicted from the cloud worker, we have to remember all of our previous state instead of recomputing. And probably final goal is flexibility of what you fuzz and what are inputs requires us to allow the user to redefine what does it mean to execute your thing and what does it mean to mutate your input. This is roughly all modern targets support anyway. Back to the picture from which I started. We have Centipede has two parts. One is the engine itself, which is a separate binary, which orchestrates mutation, execution, and maintains the corpus. And we have a smaller library that links to your executable, which gives you the coverage instrumentation. So the runner, it allows you to consume a batch of input, feed it to the target, report coverage back. And this is what we can replace. So the engine is the core tool that is one for everyone, but the runner is something you can replace for your language, for your special project, or whatever. Next, we define a concept of coverage features and the concept of feature domain. So a feature is just an integer, 64-bit integer, which uniquely represents some small behavior of your program. And the typical one would be this edge has been executed, or this this element of a constant vector has been accessed at this program counter. This would be an example of a feature. And the feature domain is a way to group features of the same kind, such that all control flow edges is one domain, all data flow edges is another domain, and so on. And currently, this domain is a fixed integer range of 2 to 27, just a random number. So the job of the runner of Centipede is to convert an input to an array of features. This is as simple as is. So your target now is an abstract entity where you feed inputs and it produces arrays of numbers. And we currently support this number of features. Since the talk is about rich coverage features, this particular slide is very rich. I apologize for lots of text. The obvious one is control flow. The less obvious are call stacks and bounded paths and PC pairs. So these things are based on control flow, but they're much more rich. PC pairs is a quadratic feature. Call stacks and paths are exponential features. And of course, to make it work, we compute the thing, then compute a hash of the thing, and then take 27 bits of the thing. So it is actually limited in the number of things that can generate. Then there are also what we call CMP features, something derived from a comparison instruction and the data that is fed into it. But then it also uses call stacks or paths as your context, and so it is also exponential. We obviously have edge counters as FL libfuzzer. We have some limited way to collect data flow arcs in your program, and we want more of those. And we have a way for a user to define their own feature domains. And in our SiliFuzz land, an example is we want an opcode and a CPU opcode multiplied by the bit it changes in the register state. So you get this kind of quadratic behavior as an integer. That's one of the ways to do custom features in Centipede. Answering Ellie's previous question, the first things that generated us new bugs were paths and PC pairs combined. We don't know which one was the most important. And the second batch of bugs was received from CMP features. So when we started aggressively using data flow that goes into comparison instructions, that kicked in more bugs. So now we somehow need to do a lot of compute now because we have very large corpus. So our corpus is sharded, our execution is distributed. What does it mean? First of all, we implemented a pretty basic file format that allows us to append data to files, and that works on a remote file system. That's not rocket science, very simple. So every file that Centipede deals with is a collection of blobs to which you can append. And the corpus of Centipede is represented as on a network disk as n shards, where each shard is two files. One file is just the inputs, where we keep appending inputs, and the other shard is the sets of features that correspond to the inputs, and we have to store the hash of the input to build this correspondence. Then, of course, since we have n shards, we have to have n workers that update these shards. Each worker only updates its own shard, but it peeks into adjacent shards. So if one worker found some interesting coverage, then eventually, over time, other workers will pick it up, but not immediately. And if a worker restarts, which in cloud environments happens all the time, like we're getting evicted, we're getting restarted, etc. If the worker is restarted, it reads the state from network disk and doesn't have to recompute anything that it knew before. And one important thing to notice here is that out of these n shards, none of the shards have the full corpus. It doesn't have all the full knowledge. Every shard has a subset. I'll not mention guided mutation here. It's a separate interesting topic. The corpus management in Centipede is perhaps the core of the logic there. And despite it being a core, it's something written in 200 lines of code probably. And this is the next big topic of research. So what does corpus management do? Remember, runner is an abstraction that converts your input into an array of features, an array of integers. And if you have some amount of inputs and some amount of possible features, then the amount of this data is a multiplication of number of inputs by number of features. And both numbers are pretty big. So remember, we want both to be in billions. So billion squared is a pretty decent number. You don't want to spend this many bytes. And so the engine, when it receives all this data from the runner, it only preserves a subset of this data. It counts the frequencies of every feature, and once a feature becomes frequent, like more than 100 appearances, it starts ignoring it.
The feature is one specific index in the domain, or is that like that domain already has 10,000 features in it?
The feature is a specific index in the domain. So once we have seen a feature 100 times or n times, after that, we treat it as frequent, obvious, and uninteresting. And so we start ignoring it. And so when we store an input alongside an input inside the corpus, we only store the infrequent features. And so the storage and memory requirements here are linear by the number of inputs, but they do not depend on the number of features. That is a fixed constant, which is currently 100. And so the engine inside the memory and on disk as well has this information. These are the inputs, and these are the infrequent features that correspond to each input. And based on this information, the engine needs to assign weights to the inputs, and those weights are used to choose what to mutate. The higher the weight, the higher the probability that we want to mutate that thing, and what to evict from the corpus. So if something has a very low weight, it is more likely to be evicted from the corpus because the corpus in memory cannot grow indefinitely. And like this, I think this is one of the core pieces of the logic. And this is literally a single function that fits on the screen, and it needs to be improved. And I think this is where ML would be a very, very good technology to improve it. Of course, at some point you want to combine all these shards on a distributed storage into one corpus. We call it corpus distillation or corpus minimization. This is a pretty basic set cover problem. We take all the shards and we minimize the set while preserving the total coverage. One important thing to remember here is that with Centipede, corpus distillation is a I/O bound task. It doesn't require your target to be present. And so this is basically download all the files one by one from the network storage and do some bit twiddling with it. So how about Centipede versus SiliFuzz and DFL? The short answer, I have no idea. And so far, I didn't even care too much. I will care about it relatively soon. If you compare Centipede with just the basic coverage instrumentation with SiliFuzz or AFL, it's probably going to be worse. And in fact, our colleagues from FuzzBench tried it and found that on some benchmarks, Centipede and SiliFuzz are similar, and on some, Centipede is much worse. And we know at least one reason why this is so. We just didn't implement some of the things that SiliFuzz and DFL have, such as memcmp, string CMP comparison, interceptors, and logic that uses it. But we'll get there. If you compare Centipede that uses rich coverage with SiliFuzz and use the benchmarking that was built for evaluating SiliFuzz and AFL, you'll also find that Centipede is lagging behind because Centipede goes wide with rich coverage. And if you use shallow coverage, the engine goes deep, and your measure of success is depth, right? Given that measurement, Centipede will probably lose on a short distance of several days of fuzzing. However, on FuzzBench, most of the things with fuzz, they saturate after a few days. While with rich coverage, Centipede doesn't saturate. It keeps finding new things and building this breadth. What is important for us, and this is not an A/B comparison, this is just our business need for Centipede. It works well for huge targets. The biggest target that is currently constantly being fuzzed is a CPU model. I cannot tell what specific CPU model that is, but it has 75 million what we call toggles. You can think of toggles as a close equivalent of control flow edges, but it's an RTL source. So 75 million features that come from toggles. It running 10,000 concurrent shards for weeks. And speaking of what you mentioned earlier today, you said 15 seconds is slow. Haha. So our speed is about 30 seconds per input, which is one of the reasons we need so much compute. And this
10K shards, does that also translate to 10K boxes or CPUs or something? Just the files that we
10K files, 10K worker threads, and just the implementation detail of our system that we run 16 threads on a single VM. But this has nothing to do with Centipede, it's just the way it's cheaper to run on our cloud system.
No, I mean, just like that runs on.
Divide this by 16, divide this by 16, this is how many 16 core VMs we have.
So like that's basically 1-to-1.
Yes, this is number of cores, precisely. This is all my slides except for the one where I've shown to my other daughter and said, hey, younger one have drawn the Centipede. Now I challenge you, and this one is much more aggressive and more bug eating. I'm almost out of time, but please questions.
It is my understanding that the huge feature map is implemented in like a gigabyte size. It is my understanding that the huge feature map containing the billions of features is implemented in a huge gigabyte sized-ish, maybe bit array that you're not resetting once per input, right?
So this is not a bit array, but a byte array because we count frequencies. We need to count frequencies which are up to 255. We limit it to 100. So it's a byte array. It is indeed huge. We have a dozen feature domains, each of them 227 bytes. So this is how many gigabytes you get. But we map it with map no reserve. So if you are actually only using shallow coverage or subset of your domains, this is what you pay for.
Right. So my question is, how do you reset the counts? Is that why you limit the counts so that you have a generational counter or something like that? Like, how do you reset the counts without map setting everything back to zero?
So the map that you asked for is in the engine. In the engine, it is never reset. We start from it being empty and fill it in. In the runner, we don't have anything like this. We don't have a map that is humongous in size. And in the runner, the collection of those features is actually different depending on the feature. And let's say, what would be the example? So for paths, for example. For paths, we have a table of 227 bits, but it is a multi-layered structure such that if one of the bits in the range is set, we know the range where it is set. And so when you clear, I'm explaining it very poorly, but anyway, so we have this large data structure. And this large data structure knows which pieces of it has been modified. And when it needs to clear it, it goes through a much smaller data structure and clears only the chunks that were modified. So if you modify the entire thing, you have to clean the entire thing. That's inevitable. But if you have modified only a small chunk of the big thing, you clear only the chunks. And that has been one of the major optimizations, which is probably 100 lines of code total. It's not huge.
Basically, vertical tracking and written.
Just manually written. Yes, I actually tried to use Linux dirty pages, and it almost worked. And then I decided that almost is not enough, and I ditched this code. Yeah. How much time do we have for questions?
Maybe.
Thanks for the talk. I was curious, when you said that for in your corpus management, you started discarding inputs that were saved for covering things that are like super frequent, right? So then you only end up with the infrequent one. So how much compression do you get? How small does the corpus become after you do all the discarding? So in the steady state, let's say you're fuzzing for days, for weeks, how large is the corpus? It's not going to be millions because you're discarding a lot of those. So what order of magnitude you end with?
So we count the frequencies of features, and as a feature becomes frequent, we start ignoring this feature. Now, a corpus elements may have multiple features assigned to it, and if some of them become infrequent, some may still continue to be infrequent. But eventually, for initial inputs you have in the corpus, all of the features there may become frequent, and then we discard that input completely from the corpus. Now, if you have a lot of rich features, your corpus will still grow infinitely. And so we just limit it with 100,000 in memory. On disk, we never remove it. So the corpus on disk grows indefinitely. Corpus in memory is limited with basically what you can fit on your VM.
So what order of magnitude is that? Is it thousands, millions?
100,000 is the default limit, which works most of the time. That's per shard, but every shard makes independent decisions, random. And so every shard has a subset of its of the full corpus.
Kostya, I was wondering, if you could comment more about the fuzz bench kind of benchmark. So you say like typically don't see like a benefit to this switch college signals, but how much of these experimented with these different types of signals? What do you think are the opportunities there?
We experimented little enough that I would probably say we didn't. And it's not that I'm not interested in that, it just haven't been my focus so far. But now that we have merged Centipede with FuzzTest, and FuzzTest in the business of competing with SiliFuzz because we want to completely eradicate SiliFuzz in our own ecosystem, we will have to do it.
Thank you.